Making physics understandable. Potential energy in a spring. We'll be using Hooke's constant. Whether a spring is stretched or compressed, there is an energy that is needed to cause the stretching or compression. Here we have a relaxed spring. We put a weight to it, it's going to stretch. When a spring is stretched at amount x, a force is needed to perform the stretching. The force is proportional to the amount the spring stretches. The proportionality constant is called Hooke's constant, and the force is given by Hooke's law to be F equals kx. The amount of work or change of energy of the spring is the average force times the displacement of the end of the spring. So we take the work as the change of energy of the spring, and it's going to be half the force, 1/2 kx, times x. Why do we use 1/2 the force? Because when we start stretching the spring, it don't take much force at all. If we stretch it halfway, it's 1/2 kx. The flow extension is kx, so the average force needed over the path of stretching at x is 1/2 the force. So the potential of the spring is 1/2 kx squared. If we were to use calculus, the work needed to stretch a spring is the integral of f dot dx, which is the differential of the displacement. That gives us a scalar, kx for the force, dx from 0 to x, and so we have 1/2 k, and the integral of x is x squared over 2, so here's the x squared. That's where the 1/2 comes from, the x squared over 2, and here's the x squared. So the potential energy the spring gains is 1/2 kx squared. While the expression reminds one of kinetic energy, 1/2 mv squared, the equation gives the potential energy of a spring. An example. A spring is stretched 2 centimeters by a 3 Newton force. How much energy is given to the spring by a force that stretches at 8 centimeters? Well, first we must calculate the spring constant, and that's when we're going to use the fact it was stretched 2 centimeters by a 3 Newton force. So 3 newtons equals K times 0.02 meters, or K is 150 newtons per meter. We would use that value. The work is 1/2 K, 150 newtons per meter, times the stretch 0.08 meters squared, or 0.48 joules. Recall that 1 joule equals 1 Newton meter.